In this presentation, we are going to look at the negative binomial distribution and how it is used to characterize the Poisson-Gamma mixtures that will arise in a lot of insurance problems in actuarial studies. So, the number of claims in a year for each insured in a large portfolio has a Poisson distribution with mean lambda. Okay, so that's the Poisson mean lambda. Okay, now quite often the Poisson mean is a constant value in a lot of problems you might have encountered before, but in this case it is actually a gamma random variable. Okay, gamma distribution with mean 0.75 and a variance of 0.5625. Determine the proportion of insured that are expected to have less than one claim in a year. So that is what is the probability of the lambda being less than 1. Okay? So this just requires a bit of lateral thinking, actually, what the question is actually about. In the first instance, what's the probability of lambda less than or equal to 1? That's what we're just asked here. But let's actually just sort of take a broad view here. Consider the population of all insurance policies, which is comprised of countless subgroups. Okay? So just a countless number of subgroups in the population. Each of these subgroups can be considered as having their own expected number of claims, i.e. their own specific value of lambda, and lambda here is a real number. So just remember that. Okay, so it could be 0.75. Actually, sorry, here I talk about it. The claims rate has from one subgroup could have a Poisson distribution of 0.25, whereas other groups could have different values, for example 0.4, 1.20 or 2.8. The distribution of these Poisson means is a gamma distribution, or in some cases an exponential distribution, which we're going to be specifically interested in here. I'm giving the game away a bit there, but just actually in the main part, for the main we are interested in gamma distributions. But just as a quick remark, the exponential distribution is a simplification of the gamma distribution in certain circumstances, and we might come across those circumstances in this case, and we will. The overall distribution of the number of claims is a negative binomial distribution. Okay, the Poisson-Gamma mixture. So, this is the method of moments. This actually helps us find the characterization of the gamma distribution. We're given two pieces of information here. Just as a quick remark, this is relating to the gamma distribution. So this is the gamma mean and the gamma variance, the expected value of x, where x is a gamma random variable. This is in terms of alpha times theta. Just as a quick remark, there are other ways of characterizing the gamma distribution. There's alpha and beta, which is a different approach here. So I just picking alpha and theta here, but because it's actually slightly easier in this case, alpha and theta. But if you try it out with alpha and beta, and which is the rate parameter as opposed to the shape parameter, you could work out the problem that way as well. Just as a quick remark, this is the problem with these complicated probability distributions and combinations of probability distributions. The structuring and the notation is, you have to keep track of what you're doing. Okay. So the method of moments, setting alpha times theta equals 0.75 and alpha times theta squared equals 0.625, gives us alpha equal to 1 and theta equal to 0.75. Okay. Now, that means that the parameter lambda follows a gamma distribution, okay, with a shape parameter alpha equal to 1 and a scale parameter theta equals 0.75. So those are two important pieces of information. Okay. Now, actually, I just talked about the exponential distribution earlier on. Just keep an eye on this alpha equal to 1. Okay. So that's going to be an important thing going forward that helps us characterize this problem. So anyway, just actually take a step back a second here. In terms of alpha and theta, the probability density function of the gamma distribution is f of x times 1 divided by the gamma function of k, okay, times alpha to the power of k, okay, times x to the power of k minus 1 times e to the minus x divided by theta. Sorry, I'm not being consistent here. I just realized that what I've done there. K here is alpha. Okay, so I'll just rewrite that 1 over the gamma function of alpha times theta to the power of alpha times x to the power of alpha minus 1 times e to the minus x over theta. Okay, so I wasn't being consistent there in my notation. That's my bad. I just copied that out of notes I'd previously written and I didn't change k to alpha. Anyway, I'll progress on forward. This is interesting. What happens when alpha is equal to 1? Well, we get x to the power of 0, which is k minus 1 or alpha minus 1. So that goes there. And the gamma function of 1 is actually 0. Okay. Oh, sorry, it's actually 1 as well. 0 factorial, which is 1. So we have 1 over theta here. So the whole thing becomes 1 over theta times e to the minus x over theta. And that is the exponential distribution. Okay? Because theta is 0.75, that means it is an exponential distribution with essentially mean 0.75. Okay? So we don't even have to calculate the gamma distribution. What we have here is an exponential distribution. Okay, so that's the cumulative distribution, or sorry, that is the probability density function of the exponential distribution. 1 over theta times e to the minus x over theta. Okay, we'll come back to that shortly. I'll leave that for the time being because it's just too long. Okay, so the probability density function is what we were given before. I'll just write it out here again. 1 over theta times e to the minus x over theta, where theta equals 0.75. Now, this is the cumulative distribution function, okay? And the cumulative distribution function is probably x less than or equal to x. I'll just write it out again. Hopefully you should know this. That's small x there. This is capital X. That equals 1 minus e to the minus x over theta. Okay, should be straightforward enough. In this case, theta equals 0.75. So essentially all we have to do is calculate 1 minus the exponential of minus 1 divided by 0.75. Bit of calculator work. There we go, 0.7364. So about 74% of the insured population are expected to have less than one claim in a year. Okay, a little bit of a discussion there like that. Okay, so you don't actually have to know that the relationship between the exponential and the gamma distribution, but what you should be able to do there is just actually reduce it down a bit. Spot that the this part here is 0 factorial, which is 1, and x to the power of 0 is also 1. Okay, so you should be able to sort of spot how to reduce it there. Okay, we'll leave it there.